Good morning everyone. Welcome to our lecture talks on antennas and wave propagation. In this video lecture, we will discuss on helical antenna and its operation and its helix modes, different helix modes. The speciality of this topic is I have taken the entire concept of helical antenna in a single image, in a single picture to say. So we can easily recapture the entire concept of helical antenna through a single diagram. So it is very easy for you to understand and recollect the concepts of helical antenna in a simplest manner. So let us start the discussion on helical antenna. Here in this diagram, this is the helical antenna structure. So the concept map of this helical antenna is shown in this particular picture. So this is the structure of your helical antenna. So helical antenna comprises of one inner conductor, next one is one outer conductor. The inner conductor acts as helix and the outer conductor is acting as a ground plane. Now let me explain the geometry of this helical antenna. Before that, let me give you the introduction to helical antenna. Basically, helical antenna falls under the category of broadband VHF and UHF frequency, very high frequency and ultra high frequency ranges. The main purpose of this helical antenna is to implement some sort of communication, that too in extraterrestrial communications. That means to transmit and to receive signal into outer spaces. We use this helical antenna for that applications. Helical antenna is basically involved with circularly polarized waves. Circularly polarized waves are implemented or used in this particular communication purpose. Now let's come to the geometry of the helical antenna. In the geometry of helical antenna, a helical antenna comprises of helix, a helix of thick copper wire, a helix of thick copper wire. This is the inner conductor of the helix, and this one is structured in the form of a helix shape. Helix shape means a spiral shape to say. This is in the spiral shape. This is, see, as I am drawing here, this is in the spiral shape. Now this is the inner conductor. The outer conductor of the helical antenna acts as a flat metal ground plate. Now this ground plane is made up of sheet or of screen or of a radial or concentric conductors. A coaxial cable is there. This coaxial cable, see in the diagram, this coaxial cable has two conductors. One is the inner conductor. This is the inner conductor. Next one is the outer conductor. The inner conductor acts as a helix and the outer conductor is stretched in the form such that it can be formed like a ground plane or ground plate. The inner conductor is stretched, twisted in the form of a helix shape. This is the simple structure of the helix. Now let me give you more details about the geometry of the helical antenna. Here in the helical antenna, at this particular point to this point, this is the inner conductor of the helix, and from point B to point A, this is the neck of your helical antenna, and from here the turns, n number of turns will be there. See, this is a spacing from here to here, the spacing between one turn to the another turn, and n number of turns are there. First turn, second turn, third turn, fourth turn, fifth turn, likewise n number of turns are there. From one turn to another turn, there is some spacing. That spacing is given as S. Okay. Now at point B to point A, this we call it as neck of the helical antenna. This is length of the helix from point B to point A, and that is equal to L is equal to S divided by 2. So what is the total length of this helix? That is capital A is equal to n number of turns, 1, 2, 3, 4, likewise n number of turns, and spacing between one turn to another turn is S. So A is equal to n into S, and the diameter of the inner conductor of the helix is small d. Here it is shown. Similarly, the diameter of the total helix means from outer conductor to inner conductor. Okay, so this total helix diameter is capital D. Now length of one turn, this is one turn, the length of one turn is capital L. Okay, this is there in the geometry of the helical antenna. Okay, now at this particular point between point B to point A, here you have to give some input like feeding wire. Feeding wire is given here. Feed wire is given here. Now this is helix axial length starts from here. From where? Point A. The helix axial length starts from here actually. Okay, and this is antenna terminal. Point B is antenna terminal. Point B is at antenna terminal. Now this is about simply the geometry of the helical antenna. Now let me explain from this geometry. C is the circumference of this helical antenna, and that C is directly proportional to the diameter d, small d, and A is the total length of the helical antenna, that is N into S, where capital N is total number of turns, capital L is length of one turn of the helical antenna, one turn length, total length, small l is length from point B to point A, that means the neck of the helical, we can call simply to understanding. So the circumference of this helical antenna C is equal to pi d. C is equal to pi into d. Okay, now let us see. By changing these values, different characteristics can be obtained. That means if you change the value of the diameter of a helix, length of the helix, the characteristics obtained from the helical antenna will also changes. See here, important point is, due to the variation of the input at this particular point, the feeding effects will be there. Due to this feeding effects, the impedance of the input will be changing. Naturally, depending on the input, our impedance matching and the output of that particular antenna will be depending. Similarly, now let us understand what is the helix action. After point A, that means this particular point, after point A, the conductor lies in some imaginary space to say. So, lies in surface of imaginary helix cylinder. So, here onwards it is a three-dimensional picture actually. So, it is left into free space actually from this particular point, from point A. Up to here it is in a straight line, but from here it turns and makes the in a space. Therefore, after point A, the conductor lies in surface of imaginary helix cylinder. Basically, to understand the operation of helical antenna, it is necessary to understand what are the different modes of helix. So, helix modes are two types. First one is normal mode, second one is axial mode. Now, the normal mode is also called as perpendicular mode. Axial mode is also called as end fire mode or beam mode. We call it as beam mode. Okay. Now, let us discuss about normal mode of helical antenna. So, normal mode, I have written my own notes for my understanding. N mode I have written it as N mode, but actually it is normal mode, right? In normal mode, radiation is maximum in Broadway direction, that means perpendicular direction. And which type of polarization is used here means a circular polarization is implemented. Circular polarization is implemented. In normal mode, occurs when dimensions of the helix is small compared to the wavelength. So, let us see at this condition, NL is less than lambda. What is N? Number of turns. What is L? Length of one turn. So, if the product of these is less than to the wavelength, then only this helix mode is normal mode of helix will be operational. So, normal mode occurs when dimensions of helix is small compared to the wavelength, NL is less than lambda. And here in normal mode, the bandwidth is narrow and radiation efficiency is low. As the size increases, bandwidth naturally increases, therefore radiation also increases. See, size increased, bandwidth increased, radiation increased. So, to keep currents in phase, it is difficult to keep the currents which is there at input side and at the radiation side to be in phase. Therefore, to keep the currents in phase, phase shifters are used. Basically, phase shifters are used here. Now, in normal mode radiation pattern, how the normal mode radiation pattern is obtained? Normal mode radiation pattern is obtained due to the combination of radiation pattern of small dipole antenna and also the radiation pattern of a small loop antenna. Now let us come to the diagram. See here, helical antenna is constructed with the help of one coaxial cable. This is the inner conductor of the coaxial cable. This is the outer conductor of the coaxial cable. The outer conductor of the coaxial cable is bent such that it can be acted like a ground plane. This is a ground plane. And this is the inner conductor, and this inner conductor is twisted in the form of a spiral, or to say in the form of a helix, in the form of a helix. Now the important point what we have to notice here is the normal mode radiation pattern is, we are getting the radiation pattern from this helical antenna, that too in normal mode radiation pattern. How it is means, it is due to the combination of the radiation pattern of a small dipole antenna plus radiation pattern of a small loop antenna. Let us see, from here to here it is a dipole antenna, from here to here it is a loop. So loop antenna radiation pattern plus dipole antenna radiation pattern plus loop antenna radiation pattern plus dipole antenna radiation pattern plus loop antenna radiation pattern. Likewise, it is a series of combination of loop antenna plus dipole antenna, loop antenna plus dipole antenna. Likewise, the radiation pattern on a whole of a helical antenna is the combination of radiation pattern of a small dipole antenna plus radiation pattern of a small loop antenna. This is what we have to understand in normal mode of radiation pattern. But here one important thing is to be noticed. Here we can notice one angle called alpha angle, that is called pitch angle of this helical antenna. We can notice one angle here, this is called alpha, that is called pitch angle of this helical antenna. Now the important factor here it is, if alpha tends to 0, that means if alpha is equal to 0, then from this helical antenna, if alpha it is tends to 0, we can obtain a helical antenna, that to the helical antenna with loop type of radiation pattern. So if alpha is equal to 0 degrees, then loop antenna is obtained. Similarly, if alpha is equal to 90 degrees, helix becomes linear antenna, dipole antenna. Okay, so if S tends to 0, that means the spacing between one turn to another turn, S tends to 0, what happens? Helix collapses to a loop. See here, this is the spacing S. If S tends to 0, these two loops come closer, this loop closer, and we can appear, it appears just like one small loop. So if S tends to 0, the helix will collapse to a loop. Similarly, if S is constant, D tends to 0. What is D? This is the diameter of the total helix. If this tends to 0, what happens? All appears like a dipole antenna here. So if D tends to 0, then helical antenna becomes a dipole antenna. So radiation pattern of both are same. That means radiation pattern of a loop antenna, radiation pattern of a dipole antenna, both are same, but their polarizations are perpendicular to each other. So the resultant field means the radiation pattern of a loop antenna, the radiation pattern of a dipole antenna, both will be resulting in circularly polarized. That means circular polarization will be taking place. So now depends on the field strength ratio, amplitude ratio, we can now define different types of fields and what are the different types of fields that are arising here. Now let us see here. Alpha tends to 0 means, where is Z here? See, we have diameter D and also alpha is equal to 0 here, and for alpha is equal to 90 degrees, for S is equal to constant. What is S? Spacing between one turn to another turn. So here this one. So this is a alpha is equal to 90 degrees, then it leads to dipole antenna. If D tends to 0, that means alpha is equal to 0 degrees, then it tends to a loop antenna. That geometry is shown in these two diagrams. Now far field of a small loop antenna is, as from the electromagnetic waves and transmission line subject basic fundamentals of a loop dipole antenna, we know the electric field strength in phi direction E phi is equal to 120 pi square of I sin theta divided by R, A divided by lambda square. Let it be first equation. where A here it is area. Let us take that area here is pi d square by 4. Pi d square by 4. Now, the far field of a short dipole is, it moves in theta direction, theta component, E theta is equal to J. Since they are perpendicular to each other, so one goes in one direction and another goes to another direction. Therefore, J 60 pi of psi I sin theta divided by R into S by lambda. Second equation. This is the field strength of a loop antenna. This is the field strength of a dipole antenna. Now, if S is equal to L, what is this S and L? S is the spacing between one turn to another turn. L is the length of the dipole. That is, S is equal to L is equal to length of the dipole. Now, the magnitudes ratio of 1 and 2. First equation is field strength of a small loop antenna. Second equation is field strength of a dipole antenna. The ratio of these two is is defined as the axial ratio. Axial ratio. So, axial ratio is the ratio of electric field strength in phi component to that of theta component. So, axial ratio AR is equal to magnitude E theta divided by E phi. E theta divided by E phi. See, the resultant radiation pattern is elliptical polarization. Helical antenna will produce you the elliptical polarization. How it produces? Let us see. AR is equal to E theta by E phi. Axial ratio. Axial ratio AR is equal to E theta. If you divide second equation by first equation, we will be getting S lambda divided by 2 pi into A, where axial ratio AR is equal to 2S lambda divided by pi square d square, where in this A we have substituted this value. A is equal to pi d square by 4. Then we get AR is equal to 2S lambda divided by pi square d square. Now go for conclusions. From these, now let us go for analysis and conclusion. Axial ratio AR is equal to 0. Then the elliptical polarization becomes linearly polarization. As I said you here, the magnitudes ratio of 1 and 2 gives you elliptical polarization. Now, if axial ratio is equal to 0, this elliptical polarization becomes linear polarization. Now, let us see. Linear horizontal polarization. How it becomes? Axial ratio is equal to 0, then elliptical polarization becomes linear horizontal polarization. If axial ratio is equal to infinity, then elliptical polarization becomes linear vertical polarization. Similarly, if axial ratio is equal to 1, elliptical polarization becomes circular polarization. So, axial ratio is equal to 1, then our elliptical polarization results to circular polarization. Actually, helical antenna is intended for circular polarization. Therefore, for circular polarization, axial ratio is equal to 1. Therefore, magnitude E theta divided by magnitude E phi. So, E theta is equal to E phi. According to this, we equate these equations. 2S lambda magnitude is equal to pi square d square. Pi square d square. So, from this, we calculate what is S value. S is spacing between one turn to another turn. So, S is equal to pi square d square by 2 lambda. Therefore, here we will be getting pi square d square means pi d. Circumference C is equal to pi d. Therefore, pi square d square means C square by 2 lambda. C square by 2 lambda. So, alpha is equal to tan inverse. Alpha is equal to tan inverse pi square d square by 2 lambda into pi d. That means alpha is equal to tan inverse pi d divided by 2 pi, that is equal to tan inverse C by 2 lambda. Now, the pitch angle to get circular polarization. What is the pitch angle to get circular polarization? Means alpha is equal to tan inverse pi d by 2 lambda. That means alpha is equal to tan inverse C divided by 2 lambda. And what is the, how is the radiation mode of normal mode of helix is? This is how. So, here we have the helical antenna. The radiation pattern of this one in normal mode will be in a figure of 8 structure. This is the length of the helix. This is how we can take. So, how we have taken this geometry means, see here we have alpha angle, pitch angle alpha, and one circumference C is equal to pi d. So, we have taken this C here. Spacing between one turn to another turn, that we have taken it here, it is S, and the total length of the helix is L. The total length of one turn of helix is L. So, here we have taken. So, with reference to these three parameters, we can plot and we can calculate the other equations which are related to our helical antenna. And this diagram is the radiation pattern of the helical antenna, where it has maximum lobe in positive x direction and a small minor lobes are also seen in the other direction. This is a simple understanding of helical antenna in normal mode of operation. And this normal mode is also called as perpendicular mode of operation.